Welcome to Thermochemistry. This is Day 3 notes for Unit 8, and today we are going to be performing calculations involving heat, mass, temperature change, and specific heat. Specific heat is the amount of heat needed to raise the temperature of 1 gram of substance to 1 degree Celsius. This is a physical property that can be observed without changing the molecules of a substance. Our unit for specific heat is measured in the units J per gram degree Celsius, or joules per gram degree Celsius. The specific heat of a substance is an intensive physical property. So intensive, as a quick refresher, means it doesn't matter how much material is present. It does not depend on amount. The substance's specific heat will always be the same. So it is independent of amount. So no matter how much water you have, if you have a half a glass, an overflowing glass, the specific heat will not change. Very similar to density. It didn't matter how much of an object you had, density is intensive. So if having a lower specific heat means that a substance will be able to heat up faster. An example of this is sand as compared to water. And if you've ever been to the beach on a hot day, you've experienced this firsthand, because the sand will become very hot very quickly compared to the water and can burn your feet. So right now we're going to look at this list and think about this list right here, and we're going to look at them and order them. On a hot day, which would get hot to the touch first? So that is actually going to be the lower number. So the lower something is, the hotter it will get. So our first one is going to be gold, because gold is the lowest number on the list. Next, we're going to have iron, because it's the next lowest number. Third is going to be aluminum. Very last, I guess we skipped fourth. Okay, so technically next would be wood, but very last would be water. And if you notice one thing about the specific heats, notice that it's just like you would expect. These are all metals. Metals are very good conductors of heat. Water is a better insulator, so it's not going to conduct heat that way. So next one, a cold wind comes, which gets cooled first. Guess what? These orders match. So if something has a specific heat that is very high, it will heat up first, and then it will also cool off first. This is why if you've ever gone to like a playground in the summer, sometimes those metal slides that they make can get burning hot, but in the winter they're going to be freezing cold. So same list: gold, iron, aluminum, and last would be water. Wood would be in between. So now we're going to talk a little bit about our specific heat formula. So this is a math equation, so if you need to take a moment and get a calculator, go ahead. We're going to use this formula: Q equals mc delta T. And these are what our variables mean. Q is equal to heat energy involved, and the unit is joules. M is equal to mass in grams. C is equal to the specific heat, what we just talked about up here. And delta T is the change in temperature in Celsius. So not Fahrenheit, we don't use that in science. just like delta H, remember delta just is a Greek symbol that represents, typically in science and math, change in. So that would be our final minus initial. Okay? All right, so Q in our equation here represents the heat lost or gained during a reaction. It can be positive or negative and is expressed in joules. Joules is our SI unit of energy, so our standard unit. T is representing delta T represents the change in temperature. This we calculate by doing our temperature final minus the temperature initial. So my example is a pot of water is heated from room temperature, 25 degrees Celsius, just before boiling, okay, to 99. What is this change in temperature? So you're going to do your final 99 minus your initial of 25. And like I said, you are going to maybe want to get a calculator. So go ahead and pick one up. 74 degrees Celsius. So we're going to practice a little more with these. Okay, our initial temperature of a sample was 33 and our final is 113. What is my change? So once again, your delta T is final minus initial. So final is 113 minus initial, and your initial is 33. So your delta T is equal to 113 minus 33. So it is equal to 80. Okay, our 80. All right, example 2. Well, we'll label that. Our initial is 418 and it is cooled. So this is our final, even though it's smaller. That's okay, because sometimes it can be negative. What is the change in temperature? So your final is 36 minus your initial. What is the change? So we're going to say 36 minus 418. So our change is negative 382 degrees Celsius. It's okay if you have negative values for this. Sometimes temperatures change, not always by going up. They can go down too. All right, on the next page, you're going to see a chart that's just trying to get you familiar with identifying your variables. Okay, so the first one says, we did this one for you, it says 100 joules. That variable's name is heat energy. So, and our symbol is Q. So the page before may be helpful for this section. Okay, so I see this, roll all that here, and if I'm looking at my table before, I see that that is specific heat. So all those symbols together, that is specific heat. And specific heat is the C in this equation. All right, our next one says 200 grams. That is the M in this equation. That is mass. And its symbol is an M. All right, once again, we see this longer one with when it looks like there's a bunch of symbols in there, that's going to be your specific heat. All right, a new symbol here. We've got 585 joules. Actually, that's not new. We already did that one. That's heat energy. And its symbol is Q. And let's go to the other side. This one we haven't done yet. It is degrees Celsius. That is going to be representing our delta T. So our variable name is right there, change in temperature. Or you could write temperature change. And its symbol is a delta T. Once again, we've got a specific heat. Okay, and that is our C. And then we have another delta T, a temperature change. And our joules. Joules is the Q. Actually, that is our heat energy. And its symbol is the Q. And last one, G, that lets me know that is mass. And its symbol is M. All right, now that we can identify our variables, or you're beginning to get there, keep your chart handy. This is very useful for practicing. We're going to use these to do some examples. Okay, so these are all very similar to any kind of word problem you've ever worked before. You just read through it, and then we're going to identify our variables and plug it all in and go. So we're working with this equation, Q is equal to MC delta T. And I'm just going to start reading. A 12-ounce can of soda weighs about 450 grams. That's mass. So it weighs 450 grams. How many joules? So I like to still, I would say, box and circle. Box your givens, circle your unknowns, just like we've been doing. How many joules? So joules, once again, we're looking, that's heat energy. We don't know that. This is what we're looking for. It's a question mark right now. And I'm going to keep reading. How many joules are released when a can of soda is cooled from 25 degrees Celsius? So our initial temperature is 25. And our final temperature is 4. So our change in temperature, remember it's final minus initial, so it's going to be 4 minus 25. And if you aren't sure about working with the negative numbers, remember the calculator will do the work for you. So it is minus 21. And our C is given to us. It is 4.18. And then we can plug it all in and go. So our Q is equal to 450 times our C, which is MC delta T. So mass times C, 4.18 times our change in temperature, negative 21. Okay, so I'm going to plug that in my calculator. All right, so our Q is equal to negative 39501, and our units for this is joules. Okay, let's do another example. Okay, so I like to box and circle, so how many joules? So once again, we're solving for Q. We don't have Q. Q is equal to mc delta T. We've got a given of 250 grams, a mass of 250. Our initial is 0. Our final is 100. So it's final minus initial, so that is 100, our delta T. Our specific heat of water is 4.18. And now we can plug it all in and go. So Q is equal to 250 times 4.18 times 100. We're going to plug that all in. I'm going to get my calculator. 250 times 4.18 times 100. All right, there it is. So there's my Q. $1,04500 joules. All right, so far so good. We've just been solving for Q. Let's keep going. Okay, so I'm reading this 120 gram sample. So our mass is 120. It's absorbing, this is different. Then this many joules, 9,612 joules. So we have Q this time. And our temperature is increasing from 25, our initial is 25, to 115. So final minus initial, so final is 115 minus 25 minus our initial is 90. Our change is 90. And we are solving for, this time, we're solving for C. So our equation is still Q is equal to mc delta T. But this time we don't have this one right here. We don't have the C. So we need to move things to the other side. We have to move around our equation a little bit, do some basic algebra, right? So I like to fill out the problem. I'm going to fill in my values. So our Q here is 9,612, and that is equal to 120, which is our mass, times our delta T, which is 90, times C, which we don't know yet. That's okay, because we're just going to work through this algebra. And I'm writing out more steps than you maybe necessarily would, but I just want to show everybody so you can follow the work. So right now I'm going to multiply 120 times 90. And that is equal to 10,800. So this times C is going to give me that. So what do I need to do to just get C? I need to get everything C by itself, so that means I need to get that 10,800 on the other side. I'm going to do that by dividing. So I'm going to divide this by itself, and that means I need to divide 9,612 by 10,800 to get C by itself. So if I divide these two, I'm going to be able to solve for C. So into the calculator, I'm going to write 9,612 divided by 10,800, and that is going to equal 0.89. Now, sometimes it can be helpful, especially I was always very not confident with my algebra skills in high school, so I would often check my own work, plug it back in, and see if I could get what I expected. So if you do that, if I multiply my answer times the mass times the change in temperature, ideally I want to make sure I'm getting this number. So I'm going to try that out just to make sure I didn't make a mistake. So I'm going to say 120 times the number I just got. And this is an optional step, but I think it's always a good idea to check your work. Oh, so I did get the same answer, so I know I solved it correctly because my Q's match. All right, and one more example. Okay, the temperature of a sample of water increases from 20.8 to 40.6. So my initial is 20.8, my final is 40.6. So I'm going to do my change, my final minus initial, so I'm going to say 40.6 minus 20.8. That is equal to 19.8. Okay, so got that part. Again, I'm given Q in this one, so I'm given 5,650. I'm solving for mass. I don't have this, and I do have the specific heat, so it is 4.18. So once again, our equation is Q is equal to mc delta T. I don't have M, but I do have the rest, so I'm going to start filling that in. Here is my C, that is 4.18, and my delta T is 19.8. So once again, I have to get M by itself. So I'm going to start by multiplying these two together. Okay, so I've got 5,650 still over here. It's equal to M times 82.764. And in order, just like I did before, in order to get M by itself, I need to divide by 82.764 on both sides. And that will give me M. So once I divide these two, I'm going to have found M. Okay? And so I got a mass of 68.266 grams. And you can use that trick, like I said, to plug that in and make sure your answer is correct. All right, so that is solving for specific heats. Great job, and let's practice with our homework.